In calculus, we are often concerned with the idea of change, the rate of change. And it's not really a new idea to us, it's just that we're concentrating so much on it here in calculus. Back when we were talking about algebra and we had linear equations, we can think of the slope corresponding with a rate of change. For example, if we're talking about this graph, this is the graph of a linear equation, we can think of the change involved or described by this graph as rise over run. Rise 1 while we run 2. So in this little graph we have a slope of 1/2. And we can think of it in terms of change if we have an example like, oh, maybe this is the graph of some population change in a very small, obscure herd of elephants, let's say. And we have the number of elephants along this axis and a time along this axis. So we might have an increase of 1 elephant for 2 years. So the rate of change in population is 1 elephant per 2 years, or half of an elephant a year, something kind of like that. Well, when it comes, though, to curved graphs, the rate of change idea changes a little bit. And in fact, it changes from one part of the graph to another. For example, if we're thinking about the rate of change along this curve, then just think in terms of intervals for a moment. If we're thinking of an interval of 1 unit, then from this point to that point, just this horizontal interval, this run you see of 1, what's the rise associated with this? Well, actually it's a drop, but it's a drop of 1, 2, 3, 4, 5 units. So we're dropping 5 units while we run 1. That sort of is an idea of a -5 slope, isn't it? But so you see we have a rate of change as a drop of 5 for 1 unit. And what about the next 1 unit? Well, now we're dropping 1, 2, 3. So we're changing at a different rate over this interval, and then for this interval it's only 1. Well, the notion is that on a curved graph, the rate of change changes. Not only does it change from interval to interval, but it changes from point to point. And that's what we're concerned with here. We're concerned about the idea of identifying the rate of change at a particular point on the graph. Now consider a point like this point, and this is the point 1, 2, 3, 4, 3. So here's the point 4, 3. We'd like to know something then maybe about the rate of change at that point. The rate of change at that point corresponds to the slope of a line which is tangent to this graph at that point. Now, tangent to the graph at the point means that the line kind of looks like this. You see it just barely touches at that point. That's the notion of a tangent line at a point. Now, we would like the slope of the tangent line at that point because it describes the rate of change at that position. Now, to make that calculation, we think about this as maybe as an approximation. We can think of the idea that, well, let's just pick another point on the graph, and this is the point 5, 1, 2, 3, 4, 5, 6. This is the point 5, 6. And we could think about the segment connecting those two and the line containing that segment. You see, now the segment is called a secant, and the line then would be a secant line. The word secant goes back to the days of geometry. When you talked about geometry and you have a circle, on the circle, if you connect a couple of points on the circle, then that's a secant, and the line containing that secant is also a secant line. Anyway, the notion of secant. So let's calculate the slope here involved with this secant line. And remember that we calculate slope using the slope formula. Slope is difference in y values over difference in x values. The difference in y values is the rise idea, and the difference in x components is the run idea. Rise over run, remember, is the loose definition of slope. So anyway, we have for our slope idea, difference in y components would be, let's see, 6 minus 3. And then difference in x components would be 5 minus 4. And in the numerator, 6 minus 3 is 3, 5 minus 4, 1, so the slope then is 3. So a slope of 3 then is an approximation for the slope of the tangent line at that point. Now, but we realize that if we had chosen this point to be a little bit closer to the point 4, 3, then this secant line would shift over just a little bit and be a better approximation. And the closer we get to the 0.43, the better the approximation. All right, our discussion here is to develop a way to sort of generally generate slopes of tangent lines at particular points. So let's generalize our thoughts here. Let's generalize the situation. Let's think that, let me take out this secant line, and we're going to just pick a general point xy and talk about how we can approach that point xy like this. Right, here's the graph, and let's just call this any old point xy. I'm using this as a point, but remember this could be any point on the graph if I'm calling it xy. All right, instead of now xy, instead of using y, I'd like to use f of x. F of x is y, so I'll call this the point x f of x. And I'll pick another point, and this other point I'm going to choose. I want it to be very close here, but just for notation purposes, I'll make it up here. But it's arbitrarily close. I'm going to make it arbitrarily close to x by using this. I'm going to say this other point might be anywhere along the graph, but I'm just going to call it x plus delta x. Delta x meaning just a little bitty distance. You see, difference in x value or distance from x, I might say. X plus delta x. Now, if that's the first component, if that's the first coordinate of that point, then f of that value, that is f of x plus delta x, would be the second component, or the second coordinate. So we have the coordinates of a couple of points, and now let's put this into the idea of slope. So the slope then would be, let's see, difference in y components, remember from up here, difference in y components would be f of x plus delta x minus the other y component is f of x. And all of this is over, let's see, the first x value was x plus delta x, and this is minus the other x component, or first component is x. Now, in the denominator, x minus x go out, and we have simply delta x. Well, this kind of gives us an idea generally of what we want to do. But you know, as delta x gets smaller and smaller and smaller, see, we're talking about making it littler and littler and littler, make that distance from x very, very tiny, then as the closer we get to x, the better the approximation of the slope of the tangent line. So we want the limit, as in this situation, as delta x approaches 0. That's really what we're after, to get the slope of the tangent line to be exactly the amount that we want it to be. So let's go over here and talk about it in terms of limit. The slope then is, the slope of that tangent line is the limit as delta x approaches 0 of this fraction. It's the same fraction we had earlier. And this will give us the slope of the tangent line at a point. Okay, let's find this. Now, with a little manipulation, we can deal with this, but we do, in order to fill into this and evaluate it, we do need to know the function. And the function turns out to be, let's see, f of x is, and I have it written down over here, x squared minus 6x plus 11. And let's evaluate this f of x plus delta x minus f of x over the delta x. This, incidentally, is called a difference quotient. You may have seen a difference quotient before. But let's evaluate it according to this function. F of x plus delta x means in the f function, replace x with x plus delta x. So this x is replaced with x plus delta x. So it's binomial squared minus 6 times binomial. All right, let's go down here. Binomial squared minus 6 times binomial plus 11. All right, this is that. Okay, now minus f of x means minus this. So minus x squared minus 6x plus 11. All right, and then bring down delta x for the denominator. Let's expand further. We have x plus delta x squared. X squared plus 2 times the product, 2 times x delta x, then delta x squared, then minus 6x, minus 6 times delta x, and then the negative of all of this, the signs change and you bring down everything. Now when you do the algebra on this, kind of looks complicated because it's just strung out. It's not hard, it's just that it's strung out. So all you need to do is create a lot of space left and right when you do this, and you're going to have to do these several times, okay, as part of your homework. But just give yourself a lot of room and write legibly. And the nice thing about these is that there are a lot of cancellation opportunities. Once you get the expansion complete, then all of the terms that don't involve delta x turn out to go out. That is, this x squared, now follow me way over here, this x squared cancels with this minus x squared. Okay, so those go out. And this minus 6x and plus 6x go out. And this plus 11 minus 11 go out. And now the only terms remaining are terms that involve delta x. Well, if all of these terms remaining involve delta x, I'm going to factor that delta x out of those terms as I bring them down. And I'm going to use this term of sort of highest degree first. I have delta x squared. When I take a delta x out as a factor, I'm left with the other delta x factor. When I take delta x out of this term, I'm left with 2x. When I take delta x out of this term, I'm left with minus 6. And now I have the delta x in the denominator, so these guys cancel. And now I have evaluated that difference quotient and I get this. And now I'm going to replace this back up here. You see, all we did is the algebra of this using our function notation or the information about the function that we were dealing with. And so this part became the delta x plus 2x minus 6. Now, the limit as delta x approaches 0 means that this term goes out. So this limit then becomes 2x minus 6. And now this is the equation for the slope of the tangent line at any point that we pick. Any point that we pick. You see, this will generate the slope of the tangent line for any x that we pick. All right. There's a name for this. There's a special name for this equation, this function. This is called the derivative function, or the derivative of f. And it's noted like this, that this is f prime of x. Remember, f of x was the x squared minus 6x plus 11. This is f prime of x, the derivative function. The derivative function is just a little engine that generates the slope of the tangent line at any point that we pick. And this is the way to find that derivative function. And when we find the derivative function, we have a way of finding the slope of the tangent line at any point. Let's find the slope of the tangent line at, well, here's the point that we were talking about before. This is the point 4, 3. And let's see what that, the slope of the tangent line at that point really is. Well, the x component is 4. We're really not concerned about the y component. It's the x component of 4, so let's put it in over here. So f prime then of 4 means 2 times 4 minus 6. So 8 minus 6, 2. So the slope of the tangent line at that point is exactly 2. This is a very, very powerful tool, and a tool that we're going to use again and again. Now, sometimes when the word derivative is used, it is used to signify or talk about the derivative function. And sometimes when the word derivative is used, it's used to talk about the slope of the tangent line at a point. So whether we're talking about the derivative as a certain number as the slope of a tangent line at a point, or whether we're talking about a function is kind of important from the context of the discussion at hand. We have found the derivative function by going through this limit process. Now sometimes in this situation, it's not only important to find the derivative at a point, but it's also important to find the equation of that tangent line. You know, we have the slope of the tangent line, but it's pretty easy to find the equation of the tangent line as well. I mean, all we have to do is go back to our algebra and think about, well, gee, how did we generate equations? Well, gee, if we're talking about a straight line, you see, and we are here for this particular, for a tangent line, we're generating the equation for a linear equation. And recall that we use the point-slope form of the slope formula for that purpose. And the point-slope form was this. Now, all we need to use the point-slope form would be coordinates of a point, which we have here, and the slope. We found the slope a moment ago to be 2. So all we do is pop into this, and it drops out rather quickly. The y component is 3, the slope 2, the x component 4, and away we go. Adding 3 on both sides, we find the equation of the tangent line at that point to be y equals 2x. I'm adding 3 here, minus 5. So y equals 2x minus 5. Suppose we want to find the slope of the graph of this function at the point 2, 1. There are a couple of ways to do this. One way would be for us to proceed as we did earlier, and that is find the derivative function. And then once we find the derivative function, plug in x equals 2 into that derivative function. That is, find f prime of 2. Well, another way is to use the limit and difference quotient idea and plug in the information about the point directly. And let me show you how that works. We would start by thinking, okay, the slope of that tangent line is the limit as delta x approaches 0 of our difference quotient, which we saw earlier. And understand that this difference quotient is nothing but a form of the slope formula. You know, it's the difference in y components over difference in x components. And this delta x is just a change in x, or a very small horizontal distance, we can think of it as. And as that horizontal distance approaches 0, you see, we're evaluating the situation. So that's really all that this amounts to. Well, anyway, to get on with it, instead of going through and finding generally f of any x plus delta x, that is, in the f function, replace the x with x plus delta x and so on. Instead of taking that approach, let's take a specific approach, because we know we're targeting that point. And that point x is 2. So replace this x with 2 and replace that x with 2. And now evaluate. Well, f of 2 plus delta x means in the f function replace x with 2 plus delta x. So this becomes 2 plus delta x squared minus 3. 2 plus delta x squared minus 3. F of 2 means in the f function replace x with 2 and evaluate. Let's go do that. In the f function replace x with 2. 2 squared is 4. 4 minus 3 is 1. So f of 2 is 1. So we have minus 1. Now it's just a matter of performing indicated operations. Squaring the binomial means first term squared, that's 4. And then the middle term is double this product. So 2 times 2 delta x is 4 delta x. And then the last term is delta x squared. And then minus 3 minus 1, that's minus 4. Now notice I've already canceled the 4's here. 4 minus 4, they go out. Now I have a couple of terms involving delta x. I'm going to write the delta x squared term first when I move upstairs, and then the 4 delta x. Let's go do that. So I've just repeated the previous step, delta x squared plus 4 delta x. I can snag a common factor delta x out of the numerator. So I have delta x times delta x plus 4. These cancel, and I have delta x plus 4. Now the limit as delta x approaches 0 of this expression is simply 4. So the slope then of the tangent line at the point 2, 1 is 4. Now, if you're dealing with a single point like this, it's okay to use this limit idea with the difference quotient. Another way, though, because it's a specific point, is to use an alternate form of the same idea. It's the same idea, it's just another form of it. And I want to show it to you because from now on, every time we find the the slope of a tangent line at a point, just knowing the function, we're going to use this form. We're going to say, okay, f prime of c, that is, the derivative at a point, is the limit as x approaches that point, you see, of f of x minus f of that point over x minus c. Now, notice the use of c here, 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 here in this alternate form. And we're being very specific now with it's that the x is approaching the c. X is approaching our target point. And this almost is more visually more like what we kind of expected to see out of this situation. Rather, you know, we were looking at delta x's a while ago, and that's kind of it was kind of a strange thing for us to be looking at. And it's okay, it's a very general idea. This is a little bit more specific, and when we're talking about a specific point, this kind of makes some sense. Okay, so here's what we want to do. We're trying to find f prime at the point 2, 1, so the c value is 2. And our x's, we want the limit as the x values in our function approach 2. And this is f of x then minus f of 2. Now, notice that I just want you to see that when in replacing c with 2 here, all of the c's that made an appearance over here in the form are replaced with 2's. And what you want to do when you use this alternative form is to write the form down just like as you would any other formula, and then replace the c with a value first, and then go about the business of evaluating or simplifying. Now, all of the action in the problem is way over here, f of x minus f of 2. Well, f of x was x squared minus 3, that's from back there, and then minus f of 2, we evaluated f of 2 to be 1 earlier. And then minus 3 minus 1 is negative 4, minus 4 in the numerator. The difference of squares factors to x minus 2 times x plus 2, and all this is over x minus 2. And the x minus 2's cancel. So we have here the limit as x approaches 2 of just this expression. And as x approaches 2, this becomes simply 4. So it might be a little bit faster to do it this way. Now, let's go through the process of finding the derivative function again. I want to show you the process from the top to the bottom. We've only done it one time. And then after that, we were talking about a single point, the slope of the tangent line at a particular point. Let's find the derivative function of this function. Now, to find the derivative function, or to find f prime of x, we're using this form. Now, this is the delta x form, the limit of this difference quotient. And often in using it like this, it's valuable to go out to the side and use the information about the function and evaluate this difference quotient. So that's what I'm going to do. I'm going to take the function, I'm going to move it over here, and I'm going to take our difference quotient and evaluate. Here's the function, here's the difference quotient, and here we go. And it's just a matter of using the idea of the function notation and filling in and performing the algebra that's involved. It turns out that it's the algebra in the calculus that makes calculus seem like it's difficult. If you're good at the algebra within the calculus, you're going to do just fine in calculus. Calculus is a series of concepts that are relatively easy to understand. But when you manipulate calculus, you're really just doing algebraic manipulations. And they're just a little more intriguing or a little more challenging than they were when you were taking college algebra or elementary algebra or whatever. It's just that the problems are a little longer. So you just have to have a little bit more room and write legibly. And don't skip any steps. Okay, here we go. F of x plus delta x means in the f function replace all the x's with this binomial, so it would be binomial squared minus 2 times binomial plus 3. Binomial squared minus 2 times binomial plus 3. That's what this is all about. All right, then minus f of x means minus this, so it's minus, here it is. All right, and now let's see, squaring. Gee, it seems like we're squaring this binomial an awful lot, isn't it? Yeah, and we are. So x plus delta x all squared is x squared plus 2x delta x plus delta x squared, and then minus 2 times x is minus 2x, minus 2 times delta x is minus 2 delta x, and then plus 3, and then minus all of this. All the signs change and we bring down the terms. Now we have a big string of terms here, but the nice thing about this is that every time you do it, when you do it 50 times, you'll realize that you're looking for every term not involving delta x to cancel. Every term not involving delta x. So x squared, there's bound to be a negative x squared somewhere. Here it is. So that's basically what you're looking for. All right, the minus 2x, we need a plus 2x. There it is. And then this plus 3, minus 3, they go out. All right, so all we have is terms that involve delta x. Now, if all three terms involve delta x, then we can factor the delta x out. And I'm going to do that on the fly. I'm going to do that between this step and the next step. We can see these terms clearly. Take delta x out of this term and you're left with 2x. Take delta x out of this term and you're left with the other delta x factor. Take delta x out of this term and you're left with minus 2. The delta x's cancel here, so we have this for the evaluation. Now, we'll bring this information back over here and continue with the problem. So f prime of x then is the limit as delta x approaches 0 of, now this became what we have down there, the 2x plus delta x minus 2. And as delta x approaches 0, it goes out. So this then becomes 2x minus 2. And we can use this, this function to find the slope of the tangent line of any point that we would like to on the graph of that function. There are several conventional ways for noting the derivative of a function. We've talked about one of them, and I'll review that, but the derivative of y equals f of x can be f prime of x like this, but another way that is often used to denote derivative is dy over dx, which is the derivative of y with respect to x. That's the way this is usually read. And also y prime, which kind of makes sense too. If f prime of x, you see, is the derivative, then y prime would kind of make a little bit of sense too. And these are also other notations that are in general use. We're not going to probably use these very often, at least certainly not right now. And when we get to them, I'll mention that they correspond with what we've been using. But f prime of x, remember, is the limit as delta x approaches 0 of this difference quotient. And we can simplify this situation a little bit sometimes just to get going with the problem and not have to write this entire fraction all of the time by simply saying f prime of x or dy over dx, the derivative of y with respect to x, is the limit as delta x approaches 0 of delta y over delta x. So just another way to show the same thing. A lot of different notations that correspond with one another. Let's consider this problem. Suppose we have f of x to be the square root of x, and suppose we want to find f prime of 4, f prime of 1, f prime of 0. The interpretation of this, the way that we understand that what this means is that we are actually finding the slope of the tangent line at this point on the graph of that, and the slope of the tangent line at that point on the graph of that, and the slope of the tangent line at this point on the graph of that. So it's the idea that here's the graph of the square root of x, and for f prime of 4, we are calculating the slope of the tangent line at f is 4. 1, 2, 3, 4. Here is f of 4, the slope of the tangent line at that point, so we're actually calculating the slope of this tangent line. F prime of 1 is the slope of this tangent line. Looks like it'd be something like this. And f prime of 0 is the slope of this tangent line. Well, gee, where is that tangent line? I can't quite tell. It's kind of the last point on this graph. We'll investigate the situation in just a little bit. All right, so let's go about the problem by generating, since we have several derivatives, so the derivative at several points to calculate, we will calculate the derivative function. So we're going to use the limit as delta x approaches 0 and so forth. So let's start this way. And laying out the problem in an organized fashion is an important aspect of this. And it's part of what I'm trying to teach you. It's part of what I want you to take possession of when you do your homework and so forth. The way you display your problem is very important in terms of how you're going to understand it both now and later on. All right, so we would start with the function. The derivative is the limit as delta x approaches 0 of delta y over delta x. That was that alternative form that we used earlier. All right, now we'd like to know something about this, and we're going to, I just brought this down right here, but this part of it we want to come over to the side and simplify. We're thinking of our function is the square root of x. We are calculating this difference quotient. So f of x plus delta x minus f of x over delta x. Now, f of x plus delta x means replace x with x plus delta x here. So this is just the square root of x plus delta x. F of x is the square root of x, and then delta x is in the denominator. Looks like we're in a bind right here. Looks like we've kind of painted ourselves into a mathematical corner, because after all, we can't just let delta x become 0. We have to manipulate this fraction somehow in order to cause us to have terms in the denominator that do not go to 0, so that we'll have a defined kind of fraction. Well, we can accomplish that here, and often we can do that when fractions involve radicals by rationalizing. And in this case, we're going to rationalize the numerator, and we're only rationalizing the numerator to kick some terms down into the denominator effectively. So to rationalize here, we're going to multiply by a form of 1, and the form of 1 that we're using is this same binomial except with a different sign. So we're going to multiply by the square root of x plus delta x plus the square root of x. And then the same amount in the denominator, square root of x plus delta x plus the square root of x. And parenthesis all around the binomials will help make sense of the multiplication. So let's see, first term times first term, the square root of this times the square. That's this term squared. When you square a square root, you get the radicand. So I'll bring down the x plus delta x. And then you know the middle term goes out because we're multiplying the sum of two terms times the difference of the same two terms. The middle term goes out and we have the last term squared. Well, the square root of x squared is simply x. And in the denominator we have delta x times this. And then in the numerator, the x plus delta x minus x. When we drop the parenthesis, these x's will take each other out, and we'll have simply delta x. And then the delta x cancels with this delta x, and oh happy day, we've gotten a nice cancellation that we were looking for, and this is the fraction that comes out of this. All right, let's bring this over here. That's the evaluation of the difference quotient. So now we have the limit as delta x approaches 0 of 1 over square root of x plus delta x plus delta x, plus the square root of x. Now, as delta x goes to 0, this rascal goes out. We have the square root of x plus the square root of x, or in the denominator, we have 2 the square root of x. So here is our derivative function. Here is our derivative function. Now, with the derivative function, we can find f prime of those numbers that we talked about earlier. F prime of 4 means in the f prime function, replace x with 4. So replace this x with 4. We have 2 times root 4, or 2 times 2, 4 in the denominator, so 1/4 is the slope of the tangent line of the original function at 4. And then f prime of 1 means in this function replace x with 1. So we would have 2 the square root of 1. 2 times 1 is 2, so 1/2. And if the x is replaced with 0 for this other one, then we have, let's see, 2 times the square root of 0. Square root of 0 is 0. 2 times 0 is 0. 0 in a denominator makes this undefined. Let's come back and interpret these over here. We found f prime of 4 to be 1/4. So that means the slope of this tangent line is 1/4. Kind of looks like it, doesn't it? A rise of 1, run of 4. That's an interpretation of that. Let's see, f prime of 1, the slope of the tangent line at 1 is 1/2, rise of 1, run of 2, looks about right. And the undefined slope, now what is an undefined slope? Remember that a line that was vertical had a slope that was undefined. So really we can think of the slope of the tangent line as being just vertical here for this particular point. We'll have a little bit more to say about continuity because it kind of comes into play right here. We're at the very end of the definition for our function here, and we need to call attention to what happens in those situations, and we'll come back to that in just a little bit. Right now, though, we'd like to go to the graphing calculator. I'd like to show you how to make these calculations for the derivative at a point on the calculator. We're going to calculate derivative on both the TI-83 and the TI-86, and it turns out on both calculators that we can take kind of a geometric approach with the graph as well as an algebraic approach. Let's go through the routine for the geometric approach first. On the TI-83, I have already entered the function and I have made these window settings. And for no particular reason. The x min and max were chosen to give friendly values when I cursor left and right, and the y min and max were chosen just to contain our function in a sort of a visually desirable position. Here's the graph. Now, to find the derivative at these various points that we talked about, we're going to go into the menu, which is the second function on trace. That's CALC. So I'm pressing second and then the trace button. And it allows me to select item number 6, which is dy dx. And now the calculator is sort of requesting a position on the graph where I want to calculate the derivative. And one of those positions was at x equals 4. So here we go. And now notice that it's making a calculation down here at the bottom. So we're just selecting the point on the graph, and the calculator is making the calculation of derivative at that particular point. And that really is all there is to it. And we can do that for the other points as well. I'm pressing second and then trace and then item number 6. And I'll just trace on over here to, I think our other point was 1. One of the other points was 1. And pressing enter, there is the derivative, 0.5. Now, due to the way the calculator is making the calculation, we get a rather long decimal down here. But to 1 or 2 decimal places, this is a precise derivative. Anyway, let's see. Let's go to the third point and see what happens. Now, recall that before we got the derivative at 0 was undefined. Let's see what the calculator has to say about that. It says non-real answer, and that's about what we expected. Yes, we get a non-real answer, an undefined amount, you see, for this value. So I'll press enter, and we're back at our home screen. Well, so much for the geometric approach. By the way, from the graph, just understand that we're finding the derivative at a point. We're not actually calculating a derivative function here algebraically with the TI-83. Nor will we do that with the TI-86. The notion of derivative is derivative at a point, which manifests itself as slope of the tangent line at a point. At any rate, let's quit out of here and look at the algebraic approach. There is a way to access a menu. It's in the math menu. I'm pressing math, and then I want to access item number 8. It's this one, inderiv, pressing enter. Now I need to enter the expression for the function. So it's the square root of x here. So I'll enter second and then for the square root of x, and I'll close that parenthesis, and then a comma. And the protocol calls for us to enter the variable that we're talking about here, and that variable is x in this expression, and then a comma and the value at which we want to find that derivative. So we have several things to enter, and then I close parenthesis, press enter, and here is the derivative at that particular point. To enter other points, instead of having to go through the routine of writing all of this again, I can press second and then enter, and it will give me back the item that was up here from before. And then from there, I can cursor back. I can just kind of go with the left arrow key and cursor back to the place where I want to change something in this expression. And I want to change this to a 1, and then pressing enter, and it will give me the derivative at that point. And then I could do the same thing for 0. And in fact, let's go ahead and do that. Let's see what it says about 0 at this position. Here's 0, enter. Aha, non-real answer. That's exactly what we expected. Okay, so all of this for finding derivative, both using the graph and using a rather algebraic approach. Incidentally, there are times when the expression here that we want to find the derivative at a point of is much more complicated than this. And sometimes if we're going to do multiple derivatives on a complicated expression, one way to do this is here's a little bit of trickery. Now remember that expression is already entered as y1. So enter the expression. Let's say it's really complicated here. It's a long-winded situation. And now placing it in this position gives us a name for it. We can actually, it's called y1 here. So what we could do, and I'm quitting out of here, and then I'm going to go second enter. And what I'd like to do, I'm going to change this part to 4, but I'm going to, instead of entering the square root of x or the expression like this, I'm going to delete this, and I'm going to enter this as y1. And y1 is found in the vars, and I want y vars, so I want to go over here. I cursor to the right to have the icon on y vars, and then I do want a function, so I'm pressing enter, and I want y1, so I'll press enter again. And now I have y1 x and 4, and it allows me then to find that derivative as I expected. But the key is that the y1 is just a handy little name for what could be a very complicated expression. All right, let's look at the situation on the TI-86. I'm just going to make a quick replacement here, and we'll go through it again. It's very similar on the TI-86. We'll go through the graphing situation first. Now I'm pressing graph, and notice that I have already entered the equation here, and then we can look at the graph. Let's see, I'm going second F5. Now second F5 is, you see that this is F5. F5 is select, and second F5 is to graph. So second F5 will give me the graph. And now I'm pressing more because I want some more information at the bottom of the screen. And it's the math menu I want to enter, so I'm pressing F1. And now I want dy dx, so I'm pressing F2. And now once again, you see I just cursor to the spot that I want to find the derivative of. And it's over here at 4. And pressing enter, it gives me the derivative as we saw earlier with the TI-83. Well, let's exit out of here and look at the algebraic approach. It's very similar to the way that we perform the operation on the TI-83. We want the calculation, or the calculus, or the CALC menu, so it's the second function on the division sign for calculating. And we can use either this nderiv or DER1. Either one of these will give very close approximations for the derivative. I am accustomed to using DER1, so I'll just press the F3 button. And now once again, it's the idea of entering the expression, and we could use again y1 if we wanted to, then a comma, and the variable is x, and the value, let's make the value here 1 for this one. We've already calculated the derivative at 4, and enter, and there's the calculation. So that's the routine that we can go through on both of the calculators. Let's work another problem where we're finding the slope of the tangent line at a point. So consider f of x to be x squared minus 6x plus 11. This is the original function that we had much earlier in this discussion, and the point 4,3 is a point that we talked about at that time. Now, it was this function that we originally found the derivative function for, and then we found the slope of the tangent line at this point using the derivative function. Well, instead of using the derivative function and instead of deriving that, I want to show you the process, just the algebra involved, if we're just directly finding the slope of the tangent line at that particular point. We use that alternative form, you see, of the derivative idea, and it is this, that f prime of c is the limit as x approaches c of f of x minus f of c over x minus c. So this is the alternative form, and it's useful when we're finding the derivative at a point. And you may notice that, and this is what I want you to grab or understand conceptually about these different forms, that this is a form in which you're using specific values, basically. And the other form is where we were kind of in a general mode. We were generally finding f of x plus delta x minus f of x over delta x, and just kind of massaging that a little bit and manipulating it a little bit so that we could evaluate that limit. But in this limit situation, we're using specifics. We have here f prime of 4, and I'm using 4 because it's at the point 4, 3 that we're looking for information about the slope of the tangent line. So it's f prime of 4, and in here we replace all of the c's with 4. So this c becomes a 4, that c becomes 4, this c becomes a 4. Just kind of a blind replacement right here. And then we go through and we perform the evaluation. So let's see, and all the action is over here. F of x is this, and then minus f of 4. F of 4 means in the f function replace all the x's with 4. This becomes 4 squared minus 6 times 4 plus 11. 4 squared minus 6 times 4 plus 11. And then the x minus 4 in the denominator drops out. So when the smoke clears in the numerator here, when we evaluate and so forth, we get x squared minus 6x plus 8. And then factoring in the numerator, we get these two factors. And fortunately, those binomials cancel. And then the limit as x approaches 4 of x minus 2 becomes 4 minus 2, or 2. So f prime at 4 is 2, as we found earlier using a different method. Take a look at this graph. We're going to examine the derivative at this point. And, you know, derivative at a point means the slope of the tangent line at a point. How do you draw the tangent line at this point? Well, let's examine the situation like this. We'll take the function, and its f of x is the absolute value of x squared minus 9. And we're going to evaluate f prime of 3. And f prime of 3 is evaluated by using this f prime of c idea, and in place of c we'll pop in a 3. So in place of the c, a 3 makes an appearance. And now let's evaluate. F of x is this absolute value expression, and f of 3 means, let's see, f of 3, replace x with 3. We have 3 squared 9, 9 minus 9, 0. So f of 3 is 0. And in the denominator, x minus 3 just comes right down. Well, we have this, and it turns out that in order to deal with the absolute value expression, we need to think about what's going on as we approach 3 from right and left. So we'll think about this limit as x approaches 3 from the right and as x approaches 3 from the left. Let's look at it up here. The limit as x approaches 3 from the right of this. Now, we need to look at it in the two different ways, because as we approach from one side, we're taking the absolute value of a positive number. When we approach from the other side, we're taking the absolute value of a negative number. When x is a little bit bigger than 3, x squared is a little bit bigger than 9. And when we subtract 9, we have a positive value. So the absolute value of the expression is the expression itself. So as we approach as we approach 3 from the right, this becomes this. All right. And now it's pretty easy to evaluate. X squared minus 9 factors this way, and now we get the cancellation as expected. And the limit as x approaches 3 of x plus 3 turns out to be 3 plus 3, or 6. So as x approaches 3 from the right, the limit turns out to be 6. Let's see what the limit is from the other side. The limit as x approaches 3 from the left. Well, from the left means for values that are just a little bit smaller than 3, x squared, square a number a little bit smaller than 3, and you get a number a little bit smaller than 9. When you subtract 9, you get a negative amount. So the absolute value of this amount will be the negative of that amount. You see, so the absolute value of this negative number is the opposite of that negative number. And that's what happens when we're approaching 3 from the left. Okay, now the x squared minus 9 still factors into x plus 3 times x minus 3. These factors go out, so we have the negative of x plus 3, and as x approaches 3, you see this still approaches 6, but it's negative 6 now. So it's 3 plus 3, or negative 6. So the limit as x approaches 3 from the left is negative 6. Let's go back to the graph and make an interpretation of what we're talking about. And it only makes sense if we look carefully at the graph. If we are approaching 3 from the right, you see, then our slope of the tangent line, our limit, turns out to be 6. But as we're approaching from this way, it looks like we're approaching negative 6. And so we say that the limit, generally, as x approaches 3, does not exist. Okay, so we can't take f prime of that point. We can't take f prime of that point. What about this one? Now, I do want you to notice that the function, the last function, was continuous, and yet it was not differentiable at that point. Okay. Here's another one, and you know where the funny point is. It's at that asymptote. And if we want to evaluate f prime of 1 for this function, then here's what we would have to do. F of x is this. Now, I tried algebraically to go through this and do the f prime of c equals the limit as x approaches c, and so on. And I got in big algebraic trouble real quick. You might try it for yourself, but you have undefined things all over the place in that rascal, and I couldn't figure a way out of it. And I knew I would paint myself into a little corner there, but it was a bad paint job all the way. So what I did is this. I found f prime of x. I found generally the derivative function, and the derivative function is this. Now, with that derivative function, I can pop in the value, the target value that I'm looking for. That is, what happens when x is 1? I want the slope of the tangent line when x is 1. Well, let's see. When x is 1, we have 1 minus 1, 0 in the denominator. You see the situation is undefined. So in this funny situation, we can't differentiate at that point where the graph is not continuous. Notice it's disjoined here. There were several situations for discontinuity, and one of them was just to have a hole in the graph, and one was to have a hole in the graph and a point defined elsewhere, and the other situation was this, where there were pieces, you see, involved in the graph, so it's disjoined. Now, the idea generally is this, that if a function is differentiable at a point C, then the function will by necessity be continuous at C. Now, but the opposite, it doesn't work the other way around. That just because a function is continuous at C doesn't necessarily imply that the function is differentiable at C. Now, we found that on the previous problem. The function was continuous, but there was just something funny going on with it. You know, it was bouncing, it had a sharp turn. And if we have, even though we're continuous, if we have a sharp turn, we're not differentiable at that particular point. Back when you took Algebra 1, you may recall that often with a section you were taught certain skills, certain manipulations, like factoring, for example. And you were shown enough examples in the instruction of that section to allow you to have an example of everything that you faced in the homework. Well, here in calculus, it's not quite like that. It is that in your homework questions, you're going to be faced with situations that you haven't seen before, that you don't really have an example for. And you're going to have to fall back on the general idea. What's the general idea in this? What are we trying to accomplish? You're going to have to ponder the situation a little bit. Let me show you a problem like that. Suppose we want to find the equations of the two tangent lines to the graph of this function that pass through the point 25. Now let's just understand the problem. All right, so we have the graph of this function. Here it is. And here's the point 25. Now, think about the two tangent lines to the graph that pass through that point. So we want lines that are tangent to the graph but go through that point. So we've got one of those lines right here, and we've got another line over here, like that. So there are two such lines that go through that point and are tangent to this graph. Now we want the equations of those lines. Wow, it's an awful lot of things to take care of all at one time, it seems like. Now, you might, if you're inclined to do so, you can stop the tape right here and try this problem on your own. Ponder it for a little while and see if you can deal with it yourself. And what I want you to get out of this is a lot of thinking and practice in conceptual thinking, conceptualizing, and attacking the problem from several different angles and so forth. And it's by thinking like that, and even if you fail, when you find the answer, when you see what the correct solution is, you'll learn a great deal from seeing that solution and then thinking about what did I think about and what is the solution. Now, what can I do to think through it in the more logical way or conceptual way to get at the correct solution? So that's what you want to bring out of this situation, even if you can't work this problem on your own right at the moment. Although we have the tools to do so. Let me show you how the problem goes. All right, we're thinking tangent line idea. All right, well, that brings to mind the notion of derivative. So let's find the derivative of this function and then kind of go from there. So here's f of x is this. Now f prime of x we'll find by doing the limit of the difference quotient here, and as we flow through this we find f prime of x to be 4 minus 2x. Now this is nothing but a machine that generates slopes of tangent lines. All right, now, what do we want in this problem? We want the equations of tangent lines. If we want the equation of a line, then we've been taught from algebra that we use the point slope form. The y minus y1 equals m times x minus x1. But what's required in that is to have a slope and a point. It's called the point slope form. What about the slope? Gee, we don't know anything about the slope. This generates slopes of points at certain points on our graph, but we don't know what points is on the graph. But we can start with the idea that the notion of slope, you see, slope is generated by, or the equation for slope is this, difference in y's over difference in x's. All right, now slope of tangent lines, gee, the slopes of tangent lines for the graph of that function is given by this. So the slope of this tangent line, instead of being m, we can write this. You see, so slope of tangent lines is given by this. Now what about this business over here? Well, we have a point. We want the slope of the tangent line to contain that 0.25. So I'm going to let I'm going to replace this y1 with 5 and the x1 with 2. So there's the 0.25. Now let's ponder it a little bit further. What we have here is a relationship of x's and y's, and this x and this y, these are xy's. Gee, those are values that make an appearance on the f function. All right, can we make another? See, we could solve this for y right now, I suppose, and get some mileage out of that and go through that logic pattern. But a quick way to do this is this. if this is the y component of a point that lies on the graph of that function. Now think of this as y equals 4x minus x squared. Y equals that. You see, we can make a substitution in that equation down there for y. Y equals this expression, so replace that y with that expression. You see, and now we're making a couple of substitutions in order to narrow our variable down to one variable, x, and then we can solve for x. All right, so here we go. We're going to replace this y with the 4x minus x squared. I've done it up here. Here's the repetition of the step earlier. The y is replaced with 4x minus x squared. This was the f function. All right, now I'm going to solve this for x. I have to massage it a little bit. I'll multiply on both sides by x minus 2. I get this. Here's the product. On the right, I just bring down, collecting like terms, throwing all the terms on one side and so forth. I get this, and then I can factor into this, and I can solve it. X is 3 or 1. Now, what are these values of x? Well, these values of x give us, they're the x coordinates for points on the original graph. Come over here, let's look at the graph. Let me show you. This is, see, x is 3 and x is 1. All right, an x of 1, 2, 3 gives us a spot on the graph. You see, and that's the point 3, 1, 2, 3. This is the point 3, 3. So here's that spot on the graph that is on the tangent line that contains the point 25, that also contains the point 25. And the other spot, the place where x is 1, the point 1, 1, 2, 3, there's the other point that's on the graph, that's on the graph of f, and is also on the tangent line containing that point. All right. So now we've gotten some mileage out of this. Now what we're after, and it's pretty easy from here, we can find the equation of those lines, because after all we have a couple of points, and we can also generate the slope rather easily, can't we? We can generate the slope rather easily because we have a machine that's right here that generates the slopes of tangent lines at certain points. So all we need to do is find f prime of 1 and f prime of 3, and we have the slopes of those two tangent lines. Let's go over here and summarize a little bit. We found x to be 3 and x to be 1 when we went through that little equation, an equation that came from the slope formula. And f of this 3 was 3, and f of this 1 is 1. So the point 3, 3 and the point 1, 3 are points on the function of the graph of f, and they are on the tangent lines that we're targeting, those targeted tangent lines. All right, now f prime of 3 is negative 2. F prime of 1 is 2. Now, this means in the f prime function, replace x with 3 and evaluate. We get negative 2. F prime, in the f prime function, replace x with 1 and evaluate. We get 2. So these numbers are slopes of the tangent lines that we were talking about earlier. Well, now, because we have the slopes of those tangent lines and we have a couple of points on the lines, we actually have an abundance of information to use. The point-slope form calls for us to have one point in the slope. Well, we have 2 points in the slope, so we can pick either point that we'd like to use. And here, I'm using the point-slope form, and I'm going to use the point 2, 5, that point that was off of the graph, for both of these, because it just happens to be on both of them. You could use the point 3, 3 for one of them, along with the slope of that line, and then the point 1, 3 and the slope of that line, if you want to. Or you can use 2, 5 for both of them, as I did here. So the point 2, 5, I replace this x with 2 and that y with 5. And for one of these lines, the slope is 2. And I evaluated here to find this to be the equation of that line. And then for the other one, the slope was negative 2. And I also used the point 2, 5 for this one. And when the smoke clears, y is negative 2x plus 9. So here are the equations of those tangent lines that go through that point that was off of the graph of f at 2, 5. We're going to be talking about functions and their derivatives for quite a while. And it's useful for us to look at the graphs of functions and the graphs of the derivatives. And we'll be doing that as well quite a bit in the future. I invite you to do that on your graphing calculator and just to look at and interpret the two, and sometimes put the graphs right on top of one another and see if you can make an interpretation between the two. Here, let's practice that just a little bit. I have f of x as the square root of x, and here's its graph. Now just from the graph, let's see if we can construct the graph of the derivative function and see what it might look like. Now, you see, all we're doing is we're thinking about, gee, that tangent line is in here, and let's think about what the slope number looks like. And let me exaggerate this just a little bit. I'm going to make this a little steeper right through here, because what's happening is that this tangent line gets fairly steep as we approach 0 from the right. So the tangent line is steep. Now, if the tangent line is steep like this, but it's still positive, then it's a big positive number. So the graph, let's put the graph of the f prime function down here. So the graph of f prime when x is very small, you see, for very small values of x, the slope of the tangent line is a pretty big positive number. So maybe it's up here. And then very quickly it becomes a smaller and smaller, you see, number for the slope of the tangent line. So this rascal is going to come down very quickly. And now what happens? Well, it starts to flatten out. That is, the tangent line starts to flatten out, so the slope number is getting smaller and smaller and is actually approaching 0, you see, as we go out this way. So no wonder then that the graph might have an appearance like this. All right, so we can kind of analyze the situation between the graph of f and the graph of f prime by looking at the two and thinking about slope of tangent line. That's the key. Here, for f of x being the absolute value of x, here is its graph. Well, out here to the left of 0, we have a straight line. And so the slope of the tangent line, well, it's just the slope of that line. Now the slope of this line, and you know from looking at from graphing this absolute value function enough times, that this is a 45-degree angle down here, and that angle is 45 degrees. And so we have a slope here of -1. And it's -1 for every one of the values. So at every point, it's -1. That's a constant function for the derivative function. So in this interval, f prime is -1, slope of the tangent line is -1, for every value you see on our function. So that rascal comes in like this. You see, now we know that at this sharp turn, it's not differentiable, and the function is not differentiable at the sharp turn, so we don't have a defined situation on f prime. Now, out to the right, this slope is 1, you see, and so for every x, the slope of the tangent line is 1. So we have, again, a constant function over here that is at 1. So here's what f prime looks like. So anyway, you might do this on a few functions. Just kind of conjure up or try to imagine the f prime function while looking at the f function.